microgravity experiments on the response of planetary regolith to low velocity impacts.
Thanks.
You can have the next set of slides.
Yes, thanks a lot. So I'm also at the University of Central Florida. We're hijacking the podium a little bit, but I'm the last one, if I understood this well, so just hang in there. So I work at the Center for Microgravity Research here at UCF, and there we perform microgravity experiments. Amongst these, we perform low velocity impacts into regolith in the microgravity conditions. So why do we perform these low velocity impacts? So in the context of exploration, for example, so very relevant for the community here, if you want to land on a small solar system body like an asteroid, a small moon, a comet, or more accurately, if you want to dock to it, or just grab it basically, you will have to approach it at a very low velocity, and at some point you will hit the surface that is covered in this fine dust called regolith, and then we want to study what's going to happen. Is there going to be a lot of ejecta happening? Are you going to bounce off, as we saw, for example, with the Philander? And there's a couple of other also more scientific purposes to it. For example, collisions, secondary collisions of an impact on an asteroid, or impacts between ring particles inside of the protoplanetary disk. So why do we have to go into microgravity to perform these experiments? Because here are two pictures under different gravity levels. That's 0.05 G. So already a hundredth of what you have on Earth, and that's 10 to minus 3 G, so a thousandth of what you get on Earth. And you see here already these are particle trajectories. The particles behave very differently. They just go back, of course, to the particle tray. And in gravity on Earth in the lab, you actually don't see any effect if you impact this impactor here on your bed of regolith at low velocity. You see nothing happening. So we have to go under microgravity to get rid, basically, of gravity dominating the grain behavior. We want to see how the grains behave if there's just cohesion between them, basically. So the experiments I'm going to be talking about are a whole family of experiments called PRIME and COLLIDE. And it's all started in 1998 with Josh Colwell flying the experiment called COLLIDE on the Space Shuttle. So this has been going on for a whole while, and as you see, the most recent experiment, and there's one missing down here, are in 2014. The last PRIME campaign was on a parabolic airplane, sorry. And the one missing here is in 2016 in April. We actually flew with Blue Origin on their new Shepard suborbital rocket COLLIDE experiment. So here's a picture of the PRIME experiment as you put it on the parabolic aircraft. And you see these are different boxes here. And PRIME stands for Physics of Regolith Impacts in Microgravity Environments. So what are these individual boxes? Down here, you have a tray that has a door, and you fill it with regolith. And up here, you have a launcher that's spring-loaded, and you will launch an impactor into your tray of regolith. So what kind of regolith are we talking about? In the PRIME experiment, we use two types of regolith, quartz sand and the Luna Simulant JSC1. The impactors are 2 centimeter sized marbles, glass and metal usually, and we impact in the PRIME experiments speeds of 15 to 50 centimeters per second. So if there's any impact people in the room, that's very low velocity. Usually 1 meter per second is already considered a low velocity impact. So this experiment here, PRIME, flew mostly on parabolic aircraft, and I forgot to say the grains we put in there have a size range starting at 250 micrometer, and usually between 250 and 500 micrometer. So these are the kind of results that we get, and you see here, that's actually Addie Dove's hand free-floating in the PRIME box, and we impact the marble into the bed of sand in this case, it's quartz sand, and you have a nice ejecta plume. But if you vary then the kind of regolith that you put in there, that's Luna Simulant now, you see you have much less ejecta. Also, we varied the speed of the impact. You create much less ejecta, and now you have a rebound of your impactor on the bed of regolith instead of the impactor just staying there and creating a plume of ejecta. So we also perform actually this prime experiment in our very own drop tower in the lab. This drop tower is just basically a tower up to the ceiling, and we drop experiments for 0.7 seconds. You get time to just shoot one thing at another. So that's what we do here. We shoot, just like in the prime experiment I just showed, we shoot one marble into a bed of regolith, and there you don't have time to observe a nice rebound or what happens for a long time afterwards. So this limits us in the lower speeds that we can get. There we are more around 50 to 100 centimeters per second. And it's just an impactor, the bed of regolith. So here we also use quartz sand and lunar simulant JSC1, but we also had some JSC Mars 1 simulant. Same impactors, 2 centimeter size spheres, and somewhat higher impacting speeds, up to 2 meters per second. This experiment, Collide, has flown on the space shuttle several times under, like, Josh Caldwell flew it in the 90s and the early 2000s. And then most recently on the Blue Origin New Shepard suborbital rocket. We had 4 boxes on there and got a chance to get the data that I'm showing right now. So this is on the suborbital rocket, and this was our first time on a suborbital rocket, so we did not schedule the experiment at the most quiescent phase. Maybe if you can notice, it's been shaking around a little. But as you see here, we have a nice impact on the bed of regolith. So this is one with sand and a nice rebound. So we can, again, measure the coefficient of restitution that we get. And this one is with Mars 1 simulant. And you see a very different behavior already. It's much fluffier, and you get a nice ejecta plume instead of a simple rebound of your, here the energy of impact was higher and the difference amount. Oh, sorry. So what kind of data do we get from these videos that we collect throughout the years? I haven't put everything on there, but mostly what I can talk about today, you see the rebound collisions. From that, we measure a coefficient of restitution. If you input a certain energy onto the regolith, what's going to be restituted to your impactor after the impact. And then for collisions that produce ejecta, we measure the velocity profile of your ejecta particles in the plume, and then we correlate that with the speed of the impact. So here's a plot of all the bouncing data that we got from all the experiment collected together of the coefficient of restitution of an impact on a regolith bed. And you see for impact velocities at a meter, 2 meter, at a meter per second, up down to 20 to 40 centimeters per second, you get a really low coefficient of restitution. So these are the impacts where you see the marble coming back out really slightly after producing some ejecta. Actually, oops. Actually, down here, sorry. This is a transition where you start producing, at this speed, you start producing ejecta. And at lower speeds than that, you see a dramatic increase in the coefficient of restitution. So if your marble just rebounds, and if it comes in a very low speed, it's going to have a low speed after the impact, but this the energy restituted to your impactor will be higher than if you impact faster. So for the ejecta produced, so we measure, as I said, we measure the mean velocity of the ejected particles. And if we put all the data together that we got, this is the kind of plot that we get. Here's the mean ejecta velocity and the impact energy. And you see we have a spread of the graph to the left here. This is due to the fact that, for example, these data points here are from parabolic flight campaigns when the payload was still bolted to the airplane. And okay, the payload was still bolted to an airplane, and you see residual accelerations from the airplane. So you can't measure really slow ejecta velocities. But once we had a free-floating experiment, you see you can report this problem to later down here. So we have a nice, so basically the scatter to the left is not really significant. This is a measurement issue, the way we perform the experiment. What we think is actually true is this correlation here. So the results, so as I showed, we have a dramatic increase of the coefficient of restitution for impact velocities lower than 10 centimeters per second. So if you have very slow impact, you will have a very bouncy impact. So of course, we're impacting marbles into small trays of regolith. So I can't really say we told you so. It would require a lot of scaling and simulations and everything, but we have a nice example of when Philae tried to land, and Philae had dampers on its feet and still had a 0.4 coefficient of restitution when it bounced off the first time. Then for ejecta production results, between 20 and 25 centimeters per second, we see the start of producing the ejecta. The ejecta masses vary significantly depending on which grain type you have. And then we see the rough power law that I showed, that, the rough power law of the velocity, the mean velocity of the ejecta is about proportional to the velocity of the impactor. So an impact like under 20 centimeters per second would not produce a load in our experiments, right? Not necessarily on the lander or anything, but we have basically under a certain speed, we will not produce a lot of ejecta. So basically, under 10 centimeters per second, you have a very bouncy result, and above 20 centimeters per second, you produce a lot of ejecta. So you have like a good spot there between 10 and 20 centimeters per second where you can have a nice impact with not a lot of ejecta. So the next steps will be like scaling and simulation work to be able to apply these results to actual landing or docking to an asteroid. And then we need more experimental data, because from what I you saw, we used lunar and Mars simulant, but we use a lot of sand too. So we need to do more with the actual simulants, and we could use Dr. Britt's simulant to perform more experiments. We can vary the G levels too, and the grain size and the packing density. All these parameters are very interesting to be varied. Yeah, thanks a lot for your attention. And this is just to finish my talk with a picture of an asteroid level impact here. It's 0.05 G in sand.
Any quick questions? Dan, you go.
Go ahead.
Okay.
To scale the simulant up, normally what would you do? If you have to make it bigger, or you just do it numerically, because in the of a space limit up there.
So you mean the size of the grains?
The size, no, the size of the impact. Right now you're using a marble, but can you use a bigger object or something?
Yeah, so that would be one of the scaling work I was talking about. Can we actually just simply scale? Also, because the tray has a limited size for us too.
Right.
So you have certain border effects there, of course. So we would have to, from experimental data, we could calibrate a code that we're working on, and then see if we can use this calibrated code to then scale to bigger size.
Is it normally a linear scaling, or is it non-linear?
Is it what? Oh, I don't know yet. Sorry. It would be nice. We love linear scaling.
We'll have discussion time after the series here. So this raises a lot of questions about all the experiments. So let's save some of these questions for our discussion period. Okay?
Just a quick comment, which is my eye caught the particles sticking to the projectile, and I wondered if there was additional information available there.
So that actually triggered a new line of ideas, I guess. The mass transfer onto the impactor So this is very relevant also to a field we're looking into at the lab, which is planet formation. So how much do you, like, mass transfer can you have on the impactor? And can we see that in the lab? So we have a student who actually started to try and have mass transfer on an impacting marble in the lab. And it turns out for now that the cohesion is much lower, of course, than gravity. So we'll have to go into a drop tower experiment probably to study that more. Yeah. Yeah, it was a nice side, a nice unexpected side result from experiments, as we get sometimes.
Thanks, Julie.